Hello everybody. Today I'm going to teach you transformer phasor diagrams. Yes, transformer, as we had discussed earlier, is an electromagnetic device. We can draw a transformer like this. The simplified version would be something like this. So this is what we call the primary winding, and this is the secondary winding. Both are interchangeable. Primary winding, we will refer to the winding where we will apply alternating voltage, and secondary to the other end. Okay, as we know, it's a magnetically coupled device where the two circuits, primary and secondary, are not connected electrically, they are connected magnetically. Whenever a current flows in the primary circuit, because as you can see, it's a coil. So because it's a coil, a self-induced EMF will be produced here. Also, along with that, a mutually induced EMF will be produced here. Yes, and how will this be produced? It will be produced because the alternating current that flows here creates a magnetic flux. Magnetic flux, which is an alternating flux that links both these windings, and this is our high permeability core. And through this this alternating flux induces an EMF here. Also, an EMF is induced at this point. Also, you can notice that when there is no load at the secondary terminal, this current is limited by the EMF that is produced here. So whatever is the voltage is limited by the EMF that is induced here. So this current I is very small at no load. Yes, and it accounts for just the magnetization of the core in ideal case. Yes, ideal, because now we are going to consider just the ideal case. Otherwise, practically, there might be some leakage of this flux. Leakage means this flux should ideally flow only in this high permeability core, and it should not link any other part. But sometimes what happens, sometimes the leakage flux even links the winding, the conductor of the winding, or it might also sometimes the stray losses also might induce induce current even in the tank, but the such losses are very small. But now we are going to consider just the ideal case. Ideal case means a winding resistance is neglected. Okay. And what else is neglected? Just like we discussed now, leakage flux is neglected. Then leakage flux is neglected means all flux that is set up here links the secondary. And core losses. As you might be knowing, is divided into two parts: hysteresis loss and eddy current loss. Hysteresis loss is mainly due to the magnetic material that is used because of, as we had also discussed in our previous lesson, the hysteresis loop. It also accounts for some losses. So hysteresis loss is mainly related to the magnetic material that we are using. And eddy current loss, as you know, the core of the transformer that is formed, we basically make various laminations. This is a laminated core. And in the laminations, even if we try so much to minimize the losses, in fact the core is laminated in order to reduce eddy current loss. Otherwise, in the core, if we make it a completely solid core, what will happen is these small circulating currents might be formed over here, and these circulating currents are called eddy current loss, because it is completely unnecessary. So in our ideal case, we will be neglecting these losses, and we will also consider that this magnetization curve is linear. Yes. is linear. That means the core has got constant permeability. Okay. So now let's get to our derivations. This is a completely a simplified form of a transformer. As you know, a transformer is divided into core type, shell type. But before discussing that, let us first discuss the basic principle. In ideal case, we will get a primary understanding of the principle of transformer. Okay, because the basis of transformation, power being transferred from one circuit to another is our flux. So we'll consider our flux, and in fact it is our sinusoidal flux that is the main point of consideration. So we'll consider it as this phi is equal to phi m sine omega t. This will form the basis. Yes. And this is the maximum value of flux. Next, we will be deriving EMF equation. As we know, EMF is produced due to change of flux, and this is, suppose primary has got N1 turns and secondary has got N2 turns. So how much, so MMF produced here will be N1 I1. Okay, and similarly the flux, that because we have no current, so I'll not say anything about it, but the MMF that is produced is N1 I1, and EMF is produced due to change of flux. So you can say EMF that is produced will oppose the flux that is producing it. This is Lenz's law. As per Lenz's law, EMF produced opposes the cause that is producing it, and in this case it is the alternating flux, change in flux. So if we simply derive, take out the derivative, it will be omega cos omega t. Yes. So simple mathematics, I hope you are aware of. We can simply write it like this. Minus cos omega t is written as sin omega t minus pi by 2. Okay. Over here, this is the maximum value of EMF. So we can say E1 max is equal to N1 phi m omega. Okay. Then if you want to take out the RMS value of this EMF, RMS value would be, as you know, RMS value is N1 phi m omega by root 2. Okay. So this is what we derived. Also, if you want to write it in terms of frequency, this is angular frequency over here, and you can simply write it over here as root 2 pi f phi m n1. Okay, so we got our E1. Now we'll proceed to E2. Okay, just like E1 was produced due to change in alternating flux, similarly E2 is also produced due to change in the same alternating flux, and this time it links N2 turns. So it will be like this. So just like we had derived it here, there is no need to repeat it. We can simply write it is N2 omega m. Okay, let me write it here, N2 omega m pi m omega sine omega t minus pi by 2. As you can see, the only difference between this equation and that equation is the number of turns. Okay, number of turns. Okay, so we can say this is E2 max sine omega t minus pi by 2. Okay, so RMS value will again be E2 max divided by root 2 is equal to N2 phi m omega by root 2, or like we had derived it last time. Okay, E1 by E2, we can say it's equal to N1 by N2. Okay, which is both equal to root 2 pi f phi max. Okay, so or we can say, sorry, it's E1 by N1 is equal to E2 by N2 is equal to root 2 pi f omega m max. Okay. So EMF per turn in primary is equal to EMF per turn in secondary. Okay, now let's draw the phasor diagram. Phasor diagram is very simple because it's ideal case. So, and we are as I told you from the beginning of the lesson, that phi is our reference point. So we'll first draw phi as our reference, and with respect to that we will plot the others. Okay. What else did I say? I told you that EMF is first I told current produces this flux, and both so are in sync. Okay. The MMF that is produced, like in primary circuit N1 I1, that MMF produced this flux, so they are both in phase. Okay, we can simply write it as IE. This is the magnetizing current because, as you know, it's ideal case and no losses are considered. So the current whatever is present is used only to magnetize the core. Next is E1. E1 will lag flux by 90 degrees. Also E2. How? Because we have already seen through this equation that E2 lags phi m by 90 degrees. Similar for the other case also. Okay, this is our ideal case. And about V1, let's also plot V1 in this diagram, because initially I told you, what had I told you? That this is V1 and this is our current. It links E1. But as this current is used only to magnetize the core, and it is very small, this V1 is equal to E1. But since we are considering the magnetic aspect, so we will show it this way, in this direction, because V1 produces flux. So V1, we are showing it to lead both current and phi, and E1 that is produced, we are plotting it below it. Yes. And there is also another way to plot it, which is also called the circuit. According to the circuit theory, we can plot it that way. But if we plot it this way, it is more convenient. Okay, that is why we will consider this approach. For now, this is it. Next lesson we'll learn a little more. Okay, thank you.